Assalamu alaikum, dear students. As you know that we are covering nowadays electromagnetism, that is unit 12 of your textbook. Yesterday we covered the topics that were the basics of the magnetic field, the general introduction, and the force that a magnetic field offers to a current carrying conductor. Today we will proceed with the next two topics. Bismillah ar-Rahman ar-Rahim. Let us proceed now. Okay, today the main topics of your text context that we will cover today are the magnetic flux density and the magnetic force on a charge in a uniform magnetic field. It differs from the yesterday topic in the perspective that it was all about you can say a current carrying straight conductor that was a sum of or an assemble of the more than one charges or larger number of the charges there. But today we will discuss a single charge that if we make it move it towards a uniform magnetic field and it enters in the magnetic field, what effect will it cause, and what sort of the force will it face when it enters in a uniform magnetic field. The topic is very much related to the yesterday's topic. It is a sort of the extension of the concept, the charge in a magnetic field. Okay. First topic is the magnetic flux density. We are all familiar with the word density. It means a certain number or the certain quantity in the space, right? That is what we call as a density. And by the magnetic flux density, we will mean that the magnetic number of lines, number of the magnetic lines in a area, or you can say that in a space, right? That is what we call as the magnetic flux density. Magnetic flux density, it is a measure of the strength of the magnetic field. Yesterday we discussed that the greater will be the density, so greater will be the strength of the magnetic field, right? And it shows how much magnetic force is acting on a conductor, current carrying current a conductor which is carrying the current within the field. Proper definition of the flux density, you have to learn it. It is very important with respect to the short question cognitives, and that is the unit of this magnetic induction or the magnetic flux density. Unit is Tesla. SI unit is Tesla. And you can see that how do we get 1 Tesla? We get if we put in the values, unit values for all the quantities that are involved. That is 1 Newton shows the force, 1 ampere shows the current, and 1 meter shows the length of the conductor. Okay, then the magnetic induction or the magnetic flux density vector will be equal to 1 Tesla. There are also other units, right? Those units are SI unit is Tesla, and in CGS system, the unit is Gauss. It is represented by the capital letter G, but you will read the word Tesla as a unit because it is the SI unit. Okay, there are more interesting things about the magnetic flux density or the vector B. It is also known as the magnetic induction, as I have earlier told you, and it is actually the SI unit is Newton per ampere per meter, right? And the base units are kilogram per ampere per second. You can get the base units from the SI unit when we put in the values of the n, that is equal to kilogram meter per second square. And as the m will be cancelled throughout, so the remaining term will get, for the base unit you will get the kilogram per ampere per second, that is second raised to power -2 as well. And the quantity has the dimensions as given. I have resolved them. You can see the values by putting the values of the dimensions of F, V and Q. Then they will be, if we put in the values accordingly, then we will get these magnetic induction dimensions, right? Now let us proceed to the next slide, that is the magnetic force, we have to calculate the basic second topic of the today, that is magnetic force on a charge in a uniform magnetic field. Okay, can you see the figure? In the figure, you can see the cross signs there. Do you people know what this cross sign means? It means that the figure you can see on the screen, it is having an effect of the magnetic field which is directed inwards in the paper. When the B vector is inwards or the magnetic field is inwards, then we represent that with a cross. And when the magnetic field vector is means to be outward, then it will be shown up with the dot. You have seen this convention in your metric classes as well. Okay. Before we proceed to the topic, we must understand some facts that are yesterday we also covered, and you have seen that figure yesterday in yesterday's lesson as well. The first figure shows the uniform magnetic field, and then a conductor which is also having a magnetic field in the form of the concentric circles. When it enters in the uniform magnetic field, then such a fringe effect is produced within the magnetic field. A catapult, you can say as well. It pushes away or it perturbs the pre-settled magnetic field lines, and such an effect will be produced. We will see what actually happens to the charge which is entering inside. Okay, there is also another convention. As you can see in this figure, you can see that the negative charge, when it enters within the magnetic field, then it is bending towards, you can say it is bending towards the right. And but when a positive charge enters, what it will do, it will move in the opposite direction. And I think you can see the perpendicular deviation of the charge as well. The perpendicular deviation means it seems to bend in the to the 90-degree angle, right, when it enters. Okay, now let us see what are the other conditions to this effect. Okay, a moving charge in the magnetic field, it experiences a magnetic force, as we have yet read that in the yesterday's lesson, that whenever a moving charge has its own magnetic field, when it moves, the moving charge has a magnetic field, and when it enters in an external magnetic field, it will experience a magnetic force, because the both fields will affect each other. They will disturb each other, they will perturb each other. This force, it is due to the interaction between the charge magnetic field itself and the external magnetic field. The direction and the strength of the force, it depends on the charge velocity and the magnetic field and the angle between them, right? What is formula for the magnetic force? As you can see, that is equal to qvb. You will see in yesterday's lesson we saw that the magnetic force is equal to ilb into sine theta, but here you can see there is a contradiction. There is qvb. You can convert, right? When you will convert the I into q over t, you will see that such a transformation of this formula can be made, right? But to this point, at the moment, you only have to see that the magnetic force depends on the charge, that is q, that is a unit charge. If you remember, that is the notation for the unit charge. V is the velocity of the incoming unit charge, and B is the strength of the magnetic field, the inward magnetic field, and the sine theta is actually the angle. If you see, if there is a factor that when the incoming charge is actually the perpendicular to the external magnetic field, then the angle between V and B, that is the velocity of the charge and the magnetic field, will be equal to 90 degrees. What it will result? It will result a circular motion. The charge will, when it enters in the magnetic field, it will bend in a circular pathway, right? And what will, if it enters in it will move in the circular pathway. And what will happen if it is actually parallel with the inward magnetic field? What will happen? You will see that the theta then will be equal to 0. Then there will be no magnetic force, right? And it will not deviate to any direction. Rather, it will, V and B will be aligned as well. And there will be no magnetic force acting on such a charge. Okay, there are some conditions for the magnetic force. Okay, that is a very important short question, short cognitive. That is, for a magnetic force to act on a charge, these conditions must be met. That is, that charge must be moving, that it will be a moving charge having some particular velocity. No force acts, if the charge must be moving, no force acts on the stationary charge. If the charge is stationary, then no force will act on it. The velocity must be a component, must have a component perpendicular component, it must have a perpendicular component to the magnetic field, that that it the charge moves parallel to the field, then no force acts, as I have discussed in prior. Okay, vector form, you can say, in the vector form you can say that it will be represented by a vector product of the velocity and the external magnetic field. Okay, you can see the difference of the signs. First one is positive q, and in the second expression it is negative q, which shows a negative charge. Only the sign convention will be changed, or rather the magnitude of this magnetic force will remain same, only the convention will change if the charge is changed. Maximum force, that will be when theta is equal to 90 degrees. Then I have discussed in the previous slide, the force is maximum. In such case, the force is maximum and the particle moves in a circular path. I have already discussed that. And the zero force means if the theta is equal to 0 degrees or 180 degree, that is parallel or anti-parallel to the external magnetic field, then it will result FB as QVB sine theta, that is equal to 0. We say that the particle moves in a straight lines. Okay, this slide shows you can see that a charge within the field in a helical moves in a helical, not a pathway, rather than the circular pathway. It happens when the magnetic force on a charge is not 0, it is not 90, or it is not 180 in the previous conditions we have read, and it is making some angle theta, and because there is a sine theta, so the pathway will be helical rather than the circular one. Right hand rule must be there. What is the use of the right hand rule there? Right hand rule will suggest that what will be the direction of the magnetic force, right? You can see that V, it is moving inward to the B vector, and what is it is resulting of the fingers of the right hand to bend a bit, right? And the thumb will represent that, what the thumb will represent, it will actually, right thumb, it points in the direction of the force. This is how we apply the right hand rule to find the direction as well. Okay, this is all for today's lesson. The cognitive is in your book. You must read it and see if there are some points, then note down. Ask me the question. Don't feel reluctant or the hesitant to ask any relevant question if some point is yet unclear, right? I will definitely answer.